All right, geometry. We're going to talk about rotations, reflections, and symmetry today. I took your classwork packet and tried to cut and paste to make everything bigger so it was easier for us to follow along with each other. I hope it helps. Let me adjust this just a little bit. Try to get it straight. There we go. So I hope this helps. Let's go ahead and get started. Okay, our opening exercise. The original triangle labeled A, right there, has been reflected across the first line. Okay, that would be our first line, resulting in the image labeled B, right here. Reflect the image across the second line. Okay, we're going to do a very basic reflection. I'm just going to measure the distance from a vertex of one triangle perpendicularly to the other triangle. So we're about right there. And then we're, let's see, about right here. And then that last one, one, two, and an eighth, one, two, and an eighth. And connect our points. We have a pretty good estimation here. It's not perfect. You learned in previous lessons to do your reflections with a compass and a straight edge. And you'll get a much more accurate reflection. All right, we have C. So Carlos looked at the image of the reflection across the second line. Here we have the second line, and said that's not the image of triangle A after two reflections, that's the image of triangle A after a rotation. That would be a counterclockwise rotation, right? Do you agree? Why or why not? I agree. We didn't actually perform a rotation in this example, but Carlos is correct. That reflecting a figure twice over intersecting lines is the same as rotating the figure. Oops. Where your lines intersect actually gives you the point of rotation. Okay, so we reflected over line 1, we reflected over line 2. Where those two lines intersect gives us the point of rotation. Okay, let's look at the next page, or it's still the same page for you. When you reflect a figure across a line, the original figure and its image share a line of symmetry, which we have called the line of reflection. When you reflect a figure across a line and then reflect the image across a line that intersects the first line, your final image is a rotation of the original figure. The center of rotation is the point at which the two lines of reflection intersect. The angle of rotation is determined by connecting the center of rotation to a pair of corresponding vertices on the original figure and its final image. So the figure above is a 210 rotation or 150 clockwise. Let's just test that. I'm going to connect 2 points. Let's just connect this one and this one, and let's measure it. It's easier to measure the smaller angle with our protractors, so I'm going to have to subtract my answer from 360 because the angle of rotation is counterclockwise. So let's see, I am at 0, 2, I got, goodness, 149 degrees. Am I measuring the right thing? Yep, I connected a point to a point. So if you look, we're at 150 clockwise. Exploratory challenge, the line of symmetry of a figure. This right here is an isosceles triangle. By definition, an isosceles triangle has at least two congruent sides. A line of symmetry of the triangle can be drawn from the top vertex to the midpoint of the base, decomposing the original triangle into two congruent right triangles. This line of symmetry can be thought of as a reflection across itself that takes the isosceles triangle to itself. The line of symmetry can be thought as a reflection across itself that takes the isosceles triangle to itself. Every point of the triangle on one side of the line of symmetry has a corresponding point on the triangle on the other side of the line of symmetry, given by reflecting the point across the line. In particular, the line of symmetry is equidistant from all corresponding pairs of points. Another way of thinking about line of symmetry is that a figure has a line symmetry if there exists a line or lines such that the image of the figure when reflected over itself is itself. Does every figure have a line of symmetry? No. Another way you can think of this is if you just fold your isosceles triangle over onto itself, you would have, you would fold everything to be equal. It would lay on top of itself. So you would cut it in half, and one half would lay on top of itself. Which of the following has multiple lines of symmetry? Nope. This one, every time we cut it, can we fold it back onto itself? If we cut it here, it would fold onto itself. If we cut it here, it would fold onto itself. That's multiple lines. If we cut it here, it doesn't fold onto itself. Okay, this next shape looks like we could cut between every, yep, and I could even cut it right here, right there, and right there. Lots of lines of symmetry. Yep. This last one, I think right there. Do you guys see any others? Let's actually draw a few lines of symmetry. Okay, to cut something in half, it's going to be pretty simple to just do a perpendicular bisector, right? You know it's going to be, the segment's going to be in half, and the line that we cut it with will be perpendicular, so cutting everything into a perfect half. Okay, there's one. Let's see. I can still do that. A little bit big, still will work. So I just cut that into half, two different ways. Okay, let's try the next one. We'll just do a few of them, we don't have to do them all. I hope you guys are getting pretty quick at drawing perpendicular bisectors now, because we seem to do it a lot. Okay, I just have one line of symmetry. Let's do another one. Trying to find that right about there. Another one. I would have to find an angle bisector to get this one. To get, well, I actually don't. I can just connect these two angles. Okay, that cuts it into an equal piece. We have lots of equal pieces. All right, I think we get the idea, right? Okay, rotational symmetry of a figure. A non-trivial rotational symmetry of a figure is a rotation of the plane that maps the figure back to itself such that the rotation is greater than 0 but less than 360. 3 of the 4 polygons above have a non-trivial rotational symmetry. Can you identify the polygon that does not have such symmetry? So going back to this one, each one, if I rotated it, I could end up back on itself. This triangle, though, if I rotated it 360 degrees, yes, it would end up back on itself, but anything greater than 0 and less than 360, it does not have rotational symmetry. The rest of them do. When we studied rotations 2 lessons ago, we located a center of rotation and an angle of rotation. Identify the center of rotation in the equilateral triangle ABC below and label it D. Follow the directions in the paragraph below to locate the center precisely. So we're going to follow these directions right here to get our center. To identify the center of rotation in the equilateral triangle, the simplest method is finding the perpendicular bisector of at least 2 of the sides. The intersection of these 2 bisectors gives us the center of rotation. So let's do that. Okay, there's one. And let's do another one. Okay, where those cross, and we're labeling it, did it say D? I'm going to sort of erase everything else because it gets a little jumbled in there. Alright, so where were we? Hence, the center of rotation of an equilateral triangle is also called the circumcenter of the triangle. We learned about this a few weeks ago. In lesson 5 of this module, you also located another special point of concurrency in triangles, the incenter. What do you notice about the incenter and the circumcenter of the equilateral triangle? Amazingly enough, for equilateral triangles, the incenter and the circumcenter are the same. So the circumcenter is equal to the incenter for equilateral triangles. Can't spell. There we go. Okay, the incenter would be if we bisected all of the angles and got to the middle. I'm not bisecting the angles just by doing this. I'm cheating. So the incenter and the circumcenter are equal for equilateral triangles. So, in a regular polygon, how do you determine the angle of rotation? Use the equilateral triangle above. Determine the method for calculating the angle of rotation and try it out on the rectangle, hexagon, and parallelogram. Okay, so on this one right here, how would we do the angle of rotation if I rotated it to get it back on itself? Okay. Okay, to talk about the angle of rotation with this equilateral triangle right here, I just drew a circle around it so we could try to see what we're doing. So this equilateral triangle actually has 2 non-trivial. So I can rotate it once, part of the 360, and A would end up on C, C on B, B on A, and then I could rotate it again, and then a third time before I make it back to the beginning. So I can rotate it twice. That'd be the non-trivial rotations about the circumcenter D. So a rotation of 120 degrees. So from here, well, again, counterclockwise, it's hard for me to remember that, right? 120 degrees, 120 degrees, and finally 120. Okay, so I can go 3 times. How did I get that though? I said before it gets back onto itself. I can divide this into 3 parts and to get 120 degrees, 120 degrees, and then back onto itself. That back onto itself is really an important thing to remember, and it's on the next page. Hold on. This identity symmetry. So a symmetry of a figure is a basic rigid motion that maps the figure back onto itself. There's a special transformation that trivially maps any figure in the plane back to itself, which is called the identity transformation. Okay, and that's what we just did right here. So 360 got it back onto itself, but we can do the trivial rotations, the trivial symmetry to get each piece onto itself twice before we go back onto itself, which is the identity. Okay? In any regular polygon, how do you determine the angle of rotation? So we just did the equilateral triangle to determine the method for calculating the angle of rotation. So let's try it out on the rectangle, hexagon, and parallelogram above. Okay, I got interrupted quite a few times during this video, so it's been a little bit of a break. Coming back to finish it, and there's a few things that I want to make sure I pointed out really well the first time. So we talked about point D being the circumcenter of the triangle, the incenter of the triangle, and the point of rotation. Okay, we found the point of rotation by doing perpendicular bisector here, perpendicular bisector, goodness, where did we do it? It was here, yep, right there. Perpendicular bisector there. So we found 2 perpendicular bisectors, and we can use that information to actually get our rotation, our angle of rotation. So if we go from here all the way over, we're at 120 degrees. So I do know that our angle of rotation from C to A is 120 degrees. I can also figure it out because I have 3 pieces. Okay, 1, 2, 3 pieces of a full circle, and I divided it into 120. So if I move this 1, 2 times, I have, missing the word, trivial rotation. Sorry, trivial, I could not think of. But if I rotate it a 3rd time, I'm back to the beginning, which is that identity. Okay, upside down. In any regular polygon, how do you determine the angle of rotation? Use the equilateral triangle above to determine the method for calculating the angle of rotation. So I'm just going to do it for one of them. For this one, you can find perpendicular bisectors. That would give you the rotation. Here, you can use either the vertices of the hexagon or the perpendicular bisectors, either one. This one, it's a 180 degrees. We're going to take the shape and rotate it 180 degrees, and it would fall on top of each other, on top of itself again, and then rotate it one more time, and you're back to the identity, okay, the beginning. So let's do this. Okay, a little more than half. There we go. And a little more than half again. I'm actually going to go over here too. And over here. Just get both of those done at once. It's giving me the perpendicular bisector of the short side and the perpendicular bisector of the long side. Okay, so we just cut that into 4 pieces. I mean, if I made a circle around this whole thing, much smaller circle, I would show that a full circle I cut into 4 pieces would be 90 degrees. So I can get 90 degrees wouldn't give us a rotation a trivial rotation, but if we rotate it 180 degrees, we would. So it would bring this point over to this side and this point over to this side. We would do A goes to, A would rotate onto B, and C would rotate onto D, okay? We can do the same thing, doing the perpendicular bisectors of the sides, which I think I showed you when I first bisected the side. And I could do that many times. If I give you a guesstimate. Okay, I've just bisected it into 1, 2, 3, 4, 5, 6 different segments. So if I rotated one of those 6 segments, I would go from there to there. And then I would rotate again. So I could rotate with either the vertices or the perpendicular bisectors. And 6 pieces, each angle is going to be 60 degrees. So each trivial rotation is going to be 60 degrees. I can get 5 of them in before I go back to the identity. And then here, it's very much like the rectangle. It's 180 degrees to get halfway. 180 degrees would be halfway, and then another 180 degrees back to the identity. Cool. Identity symmetry we've talked about. Symmetry of a figure is a basic rigid motion that maps the figure back onto itself. There's a special transformation that trivial maps any figure in the plane back to itself called identity transformation. Okay? All right, let's try this one. So use figure 1, which is right here, to answer the questions below. Draw all lines of symmetry. Locate the rotational symmetry. So I'm going to draw the perpendicular bisectors. One more. Okay, I did the perpendicular bisector through segment AB. It's going to work through segment DC also. Right there. And then through BC, we'll go through AD also. Okay. I can also do symmetry through the angles. And that works. Draw all lines of symmetry. There is the center of rotational symmetry. Describe all symmetries explicitly. I have what's called line symmetry. So line 1 and line 2 would be line symmetry. I have rotational symmetry. 1, 2. So if I take the shape and rotate it 45 degrees, it would look the same. Okay, it would be back on itself. And then we also have the identity symmetry. How many are rotations? So I can rotate this thing 90 degrees. I said 45 earlier, I'm sorry. We're going to take this and rotate it 90 degrees for our rotational symmetry. So 90 degrees, 180 degrees, we can do 270 degrees, and then back to identity would be 360 degrees. That is 4 rotations. And then how many are reflections? We would have 4 reflections also. So I can take this shape and reflect it this way over that line symmetry. I can reflect it this way over that line symmetry. I can also do that at diagonals. I can go over the diagonal here and over the diagonal there. So 4 reflections over line 1, line 2, line 3, and line 4. That would all work. Prove that you have found all possible symmetries. Okay, we'll have to go back and refer to the drawing a little bit. How many places can vertex A be moved to can be moved by some symmetry of the square that you have identified? Note that the vertex to which you move A by some specific symmetry is known as the image of A under that symmetry. Do you remember the identity symmetry? So vertex A can actually be moved to A, B, C, or D as we rotate that around. And if we look at it right here, can't really see it, there we go. Vertex A can be moved to A, once we go all the way around, B, C, and D. For a given symmetry, if you know the image of A, how many possibilities exist for the image of B? If you know the image of A, how many possibilities exist for the image of B? So A went there. I could flip A over. All right. Prove that you have found all possible symmetries. How many places can vertex A be moved to by some symmetry of the square that you have identified? Note that the vertex to which you move A by some specific symmetry is known as the image of A under that symmetry. Did you remember the identity symmetry? So really, vertex A can be moved it can be moved to, we have to do the identity, and then it can be moved to any of the other ones, A, B, C, or D. So that would be 4 places. So now let's just look at A. So for a given symmetry, if you know the image of A, how many possibilities exist for the image of B? So if we look here, can you see that? Yep. If we know where A is, B has to be on either side of A. Even if we reflect this piece over here, B is next to A. If we reflect this over here, B is next to A. So B can only be in 2 places. That's its only possibility, okay? Now, verify that there is symmetry for all possible images of A and B. So A and B, it can go to AB, which is your identity. A and B can go to A and D, which is a reflection. So A and B can go to AD. So we're going to take this and reflect it over, which brings B down here. I didn't spell that right. Reflection along segment AC. And then we have AB can go to DA, which is different than AD, because that would be a rotation by 90 degrees. So AB would rotate to DA because it's a rotation of 90 degrees. So using parts B, count the number of possible images of A and B. This is the total number of symmetries of the square. Does your answer match up with the sum of the numbers from exercise 2, part B and C? So if we look at B and C, we got 8. And if we look here, so we have 4, 5, 6, 7, 8. Yes, it does, which is very cool. All right, your relevant vocabulary. We didn't talk about this, so it's very important that you know. A regular polygon. A polygon is regular if all sides have equal length and all interior angles have equal measure. If you look at these shapes right here, okay, this, not regular. Looks like this angle is small, this one's a little bit bigger, and this one's the biggest. Not a regular polygon because these sides are bigger than these sides. This is a regular polygon. All the sides are equal in measure and all the interior angles are equal in measure. That's another reason we also know that each interior angle is 60 degrees because it's a regular hexagon, 6 sides. We can divide that and we would get all of our interior angles being 60 degrees. This is also not a regular polygon. This angle is much bigger than that one. And I don't know if the sides are equal or not because I can't tell, and I could measure, but I'm not going to. Awesome. Okay, describe line symmetry, rotational symmetry, and identity symmetry. So first of all, let's make sure we understand what line symmetry is. When there exists a line or lines such that the image of a figure when reflected over the line is itself. Okay? So that's line. We're going to get a fresh page and do rotational and identity. Okay, the other one we had was rotational symmetry. Rotational symmetry, we'll say non-trivial, rotational symmetry of a figure is a rotation of the plane that maps the figure back to itself such that the rotation is greater than 0 degrees and less than 360 degrees. And then we have identity symmetry, a basic, rigid motion that maps a figure back onto itself. I hope you can read that. If not, you could have heard my voice. Awesome.